he started telling me about this, that I really should learn about all this stuff. Of course, if Maximo Sandin is 100% correct, this model is probably wrong because it looks too similar to Darwin's theory, maybe. That's why I wanted to talk to Sandin. But I can take at least one thing from Sandin's theory, which is if he's right, there are very high-level mutations. They're called viruses. So this was just 2 days ago that here in Madrid. So I don't know if this is correct or not, but it looks like it looks like an interesting possibility. So this I got by reading La Crisis Latente del Darwinismo by Mauricio Abdala in Espanol, even in Spanish, even though the author is Portuguese. Okay, so maybe this is not that crazy, even in real biology. If I don't know. Okay, so now here's this model. Now the only point of this model is that you should be able to prove theorems, right? It's very easy to come up with a model and then you can't characterize its behavior. So the whole point of this is that hopefully this is simple enough that we can understand, we can prove that evolution works here. Which would mean that we have a living process going. It's alive, according to John Maynard Smith's definition. So here, let me tell you what I can prove about this model. Well, the first thing you need to do, you want to measure the rate of biological creativity. You want to see how fast the fitness is increasing, and compare different regimes, smarter and stupider regimes. So to measure the rate, actually it turns out that the fitness increases very fast in this model, extremely fast, non-computably fast. And the way to measure the rate of biological creativity, or how fast the fitness increases, is using something called the Busy-Beaver function, which was proposed by Tibor Reto in his original paper on the Busy-Beaver problem. And that's sort of the winner of the Busy-Beaver problem, the best solution that you can have to the Busy-Beaver problem with a less than or equal to n-bit program. In other words, it's the fitness of the fittest program up to n bits in size. Or it's the program that does best on the Busy-Beaver problem that is up to n bits in size. It's the fitness of, it's the number named by the program, which names the biggest number, which is less than or equal to n bits in the size of the program. Okay? So the whole point of Tibor Reto's paper was that the Busy-Beaver function is a very natural definition of a function which you can prove is uncomputable because it grows faster than any computable function. And it grows faster than any computable function because if you could compute this, it turns out you can use it to bound the largest possible runtime of a n-bit program. So then you can just run the program for that amount of time, and if it hasn't halted, you know it never halts, and you've solved Turing's halting problem. So this has to grow faster than any computable function. The title of Reto's paper was something like a natural definition of an uncomputable function. Okay, so one of the things to say to put this in biological terms is to be able to calculate Busy-Beaver function of n, I would say requires n bits of inspiration or n bits of biological or mathematical creativity. That's the number of bits in the program that names the biggest number that's up to n bits in size. And to find that program, you really need to, ask an oracle or somehow be inspired and get how many bits, how many yes/no questions that you have to ask an oracle. It's n in order to be able to calculate Busy-Beaver function of n. Okay, so now let's use this Busy-Beaver function, which grows very fast. It's sort of like a super exponential function. And if you take the inverse of the Busy-Beaver function, it's like this, the equivalent of the logarithm, in this theory. It's something that grows very slow. So if you think of a log scale in physics, or a log scale, this is the scale you use is inverse Busy-Beaver function or something. Okay, so anyway, to graph the behavior. Okay, so let's look at some stupid ways of evolving, which are not Darwinian evolution, and see how fast they go. The stupidest way of all is just to do a random walk, well, just to actually to forget it's exhaustive search, to forget your previous organism and just have the mutations give you new organisms at random. But the mutation isn't told the current organism. So basically you're just fumbling over the whole space, and this means you don't remember the previous organism, and it turns out what you end up doing is exhaustive search. You actually end up covering the whole space of possible organisms, and so to get to fitness busy bee with function of n, there are 2 to the n programs up to n bits in size, and it takes you a time that grows exponentially as 2 to the n in order to get to the fitness busy bee with function of n. Because this fitness is achieved by an n-bit program, and if you're just trying all the organisms at random, in a time that grows roughly exponentially, you're going to get to that fitness. Okay, simply because this search is ergodic. You're really covering the whole space of possible organisms. Now, real biology is not at all ergodic. As Lenny Susskind pointed out to me when I gave a talk on this at the Perimeter Institute, the first thing he did after my talk was come up and say, well, is this process ergodic? Is it not ergodic? You always learn a lot by seeing how a good physicist thinks about a problem. So this is definitely not ergodic. If you look at the human genome, it's 3 times 10 to the 9 bases, so there are 4 raised to the 3 times 10 to the 9 possibilities for genomes that size, and that number is monstrously big, and the history of life on this planet is not big enough to cover anything, to cover all possible sequences that size. This number is just monstrously big. It's just orders and orders of magnitude. It's an astronomical. So you only able to cover a very small fraction of the space of possible organisms. So this is not at all. This is very stupid. This is not at all what biology is doing. Now, so this is the stupidest thing you can possibly do. Now, what is the smartest thing you can possibly do? Well, the smartest thing you can possibly do, I'm calling intelligent design, which maybe was a bad choice. It's in quotes. The smartest thing you can do is if you get to pick which mutations to try in the best possible order, one by one. Instead of picking the mutations at random, you, who've created this model and presumably can understand how it works best, you get to say, first I'll try this mutation, then I'll try that mutation, then I'll try the next mutation. Technically, you have to say that it has to be a computable sequence of mutations to try. So what is the best you can do if you pick each time the best mutation to try, subject to condition that the whole sequence has to be computable? Well, it turns out what you can do is you can get n bits of biological creativity in time that grows as n, rather than in time that grows exponentially in n. So you're basically getting 1 bit in creativity each time you try a mutation. Why? Well, because basically, a way to think about it is you're going to an oracle for the halting problem. And the oracle is basically giving you 1 bit because it's telling you, is the mutated organism fitter or not than your previous organism? And the reason that to take advantage of the oracle, the whole point has to be the question of whether the mutated organism halts or not. And if you do things right, it turns out I can show you the optimal sequence of mutations, and after trying n mutations, you will in fact tomorrow I'm going to show you that. That's the proof of this theorem, which I'm giving tomorrow of this. So the fitness will grow very, very quickly. So this is the best you can do, and this is sort of the worst you can do. This is the smartest possible thing. This is the stupidest possible thing. Now, of course, real biology, you're picking the mutations at random, right? You don't get to, unless you're a gardener or an animal breeder, and you're doing genetic engineering on an organism. But assuming that you're having random Darwinian evolution, the mutations are picked at random according to the probabilities that I described before. How will that do? Well, here's the main theorem. The main theorem is that it's not too bad. It will reach this fitness, it'll have n bits of biological creativity in a time that basically grows as n squared. it's a little bit slower than n squared, but it's much closer to n squared than n cubed. And so this is a hell of a lot faster than exhaustive search, but it's not quite as fast, fortunately, as this. I would view this model as a failure if these two collapse onto each other. And I have to admit that it's possible that they do. I can show that the fitness will get this big, will on average get this big when the time has gotten this big. Unfortunately, I cannot yet prove that random Darwinian evolution is slower than picking the best possible choice of mutations. Intuitively, it looks sort of likely, but that's not how you do pure mathematics. And it's not as obvious as it looks, because when I try to prove it, I don't find a proof. So the sort of heuristic arguments which tend to suggest that this should be slower than this, because it does look like it ought to be slower, damn it, but I can't actually prove it. It may be that I'm just stupid, or it may be that in fact that it's wrong. In fact, and this ends up being just as fast as this, or nearly as fast, and I would regard that as a flaw.